Hello! In this video, we are going to prove the following theorem. Suppose A is a set. Then A has 0 elements, if and only if A is the empty set. Okay, now before we get into the proof, let's get some context. Now, for our purposes, we are going to say that the natural numbers includes 0. And second, we're going to say for each natural number n, we define the following set. For each natural number n, we define the set In to be the set of all positive integers less than or equal to n. And remember, the positive integers is basically just the natural numbers, not including 0. Okay, now, what do we mean by number of elements? Well, what we mean is the following. Given a set A, if there exists a natural number n such that we have a bijection from In to A, then n is unique, right? N is the only possible natural number we could have that we have a bijection from In to A. And so we denote this natural number n as the number of elements in A. And that's the idea. Now, in the previous video, we proved this. And basically, it's the fact that every finite set has a unique number of elements, right? Finite sets are sets where there exists a natural number n that satisfies this condition. So if A is finite, then A has a unique number of elements. And that's the idea. So we're going to use these ideas to help us prove the theorem. And so to start out the proof, let's give ourselves a set A. And our goal is to prove this is true if and only if this is true. So we're trying to prove a statement containing if and only if. So what we're going to do is we're going to prove if this is true, then this is true, and if this is true, then this is true. Let's start by proving if this is true, then this is true. To do so, suppose this is true. So really, we're supposing that A has 0 elements. So what this means is that 0 is the natural number that satisfies the fact that we have a bijection from I0 to A. So there exists a bijection from I0 to A. I'll call that bijection F. Now, what is I0? Well, I0 is precisely this set where we replace n with 0. So really, I0 is the set of all positive integers less than or equal to 0. But wait a minute, there are no positive integers less than or equal to 0. So I0 must be empty, right? If for a contradiction I0 was non-empty, then there would exist some positive integer I such that I is less than or equal to 0. Well, since I is a positive integer, we also have that I is greater than 0. So I is greater than 0 and I is less than or equal to 0. So that gives us a contradiction. Therefore, I0 must be empty. And since I0 is empty, we can replace the I0 here with the empty set. So F is really a bijection from the empty set to A. Now, we're trying to prove that A is empty. So, assume for contradiction A is non-empty. Well, since A is non-empty, this means that there is some element X in A. However, since F is a bijection, we know that one of the things that means is that F is surjective. And what does it mean for F to be surjective? Well, this means that for every element Q in A, there is an element P in the empty set such that F of P is equal to Q. So, since X is an element of A, there is some element P in the empty set such that F of P is equal to X. But because this is the empty set, we know that every object is not an element of the empty set. So P is not an element of the empty set. So these two facts give us a contradiction. Our assumption that A is not the empty set led us to a contradiction, so we must instead have that A is the empty set. So we have proven if this is true, then this is true. Now we're going to prove the other direction. That is, we're going to prove if this is true, then this is true. And to do so, suppose A is the empty set. Now, there's another fact that we're going to rely on that I forgot to write, and it's that for every set A, there is a bijection from A to itself. So in particular, there's a bijection F from the empty set to the empty set. Well, since A is equal to the empty set, and I0 is equal to the empty set, we can replace the empty set here with I0, and the empty set here with A. So what do we see here? Well, we have a bijection from I0 to A. According to what we have written here, we have found a natural number n such that we have a bijection from IN to A. Namely, this natural number is 0. And we know that this natural number 0 uniquely satisfies this condition. So, yeah, the number of elements in A is equal to 0. So now we've proven if this is true, then this is true. And we've proven both directions of the if and only if, which means we've proven precisely this statement. So this completes the proof. And so yeah, that's pretty much it for this video.